Okay, let's start. So today we will talk about canonical forms. So the canonical forms are very important for the computer system to understand your design logic. It provides a method for the computer system to convert your truth table to Boolean functions or Boolean expressions. It consists of mini terms and max terms. It can be either written as the sum of the product or midterm, mini term, or product of the sums, or product of the max terms. And they are actually equivalent. You can convert it from one canonical form from one representation to another representation. So when the variable number are fixed, if you can write two different truth tables to the canonical form, then you can actually compare them. And you can identify whether they are the same or not. So the midterm is also called the so-called sum. Midterm are the end terms with every variable in either true or complemented form. So if one variable is false, then you can write it as in the complemented form. Given that each binary variable may appear normal, like x, or the complemented x bar, there are 2 to n midterm for n variables. For example, if we only have two variables, x and y, then we can generate 2 to 2, which is 4 combinations, which are x, y bar, x bar y, x bar, and y bar. So if we have 3 input variables, then basically we can have 8 midterm, which is 2 to 3, which is 8. So each midterm is actually related to one particular input combinations and is equal to 0 when at all other combinations. For example, the x bar, y bar, z bar is always equals to 0, except for the input combination of x, y, z, which are all zeros. So only for this input, x bar, y bar, and z bar will output a 1. So we can write the one midterm as the and then provide an index to it. So the index value is also corresponding to the combination of the x, y, z. For example, if this midterm is x bar, y bar, z bar, only when x, y, and z are all zeros, it equals to 1. So we can use the value of x, y, z as the index, which is a 0. So we can write a midterm as mi. I is actually the index of the midterm. When the x, y, z value equals to the binary form of I, the midterm can be 1. So here is one example. So for the M2, only when x, y, z is 0, 1, 0, this M2 can be equals to 1. So if you convert 0, 1, 0, this binary form to its decimal form, then it's actually a 2. Since we have 3 variables here, then totally we have 2, 2, 3, which is 8 different combinations. And we also have 8 possible midterms. So the max term are all terms with every variable in true or complemented form. So it's all about all operation. Given that each binary variable may appear normal, like x, or complemented, like x bar, there are 2 to n max terms for n variables, which is the same as the midterm. Then if we have 2 variables, x and y, we can have 4 combinations, like x or y, x bar or y, x or y bar, x bar or y bar. So there are 4 combinations. So consider if we have a circuit, it has a 3 input signal, x, y, z. So we have 3 input variables. Totally, we can have 8 max terms. So each max term equals to 0 at exactly one of the 8 possible input combinations, and is equals to 1 at all the other combinations. So max term can be 0 at 1 when the input combination will have one particular input combination. But for the other 7 input combinations, its value will be 1. For instance, if we have x or y or z, this expression will be 1 at all combinations except the combination of x, y, z when they are all zeros. So only when x, y, z are all zeros, x or y or z is a 0. So only for this particular input combination, this max term can be a 0. For all the other 7 combinations, the value will be 1. And we can write the x or y or z as the capitalized m. And then we also have an index. The index is the decimal form of the input combination, which can generate a 0. So for example, if we want this max term to be 0, then x, y, z have to be all zeros. Then if we convert this 3 0 value into its decimal form, then the decimal form is also a 0. So we write this max term as the capitalized 0. Then here are some examples. So for the capitalized, let's say 6, it can be 0 for only one particular combination. And that combination is 1, 1, 0. So only for x is 1, y is 1, and z is 0. M6 is 0. For all the other combinations, the value will be 1. So we can actually apply the so-called De Morgan law to convert the max term to midterm and convert the midterm back to the max term. So here are some examples. So in this example, I will put the midterm and the max term into the same table. In this table, the first column is the index. The second column is the midterm, and the last column is the max term. So we can see that if we apply a bar here and apply a bar on the x bar and the y bar. So if we apply a complement operation on this midterm, then we can exactly convert it into its max term, which is x or y, because of the De Morgan law. So we can see that by the De Morgan law, we can actually convert midterm to the max term if they are in the same row in this table. And there is some standard order among the midterm and the max terms. The standard order can be represented by the index I introduced in the previous several slides. And the index can be also called a subscript. The index is actually a number which corresponding to a binary pattern. So which is the the index, of course, is in decimal representation, but the decimal representation is equivalent to the binary pattern of the input combinations. So the bits in the pattern represent the complemented or normal state of each variables listed in the standard order. So all the variables will be present in midterm or max term, and will be listed in the same order in alpha beta, in their alpha beta order. So here are some examples. We will have A, all B, all C bar. So this is a standard order. Another example is A, all B, all C. So if we have a B, all A, all C, this is not a standard order because it's not in the alpha beta order. And if we only have a B, C, B and C, then it's not a standard order either. Why? Because we don't have A. You have to have all the variables in the term. Then the term can be in the standard order. So the meaning of the index of the midterm or max term are different. So for the midterm, 1 means the variable is not complemented, and 0 means the variable is complemented. But for the max term, they have a reversed meaning. 0 means the variable is not complemented, and 1 means the variable is complemented. Not complemented means the normal variable. So here is one example. We have 3 variables, x, y, and z. So the standard order is the alpha beta order. We have all x, y, and z. So the index is a decimal representation, which is a base 10. The value is a 0. Then if we convert this index to its binary form, which is 3 zeros here. So for this input combination, all 3 variables are complemented for midterm. So of course the midterm 0, the index here is a 0. Then we have x bar, y bar, and z bar. And for the max term, all the variables are normal. So no variable is complemented. So we have x, y, and z here. So the capitalized M0 is the x or y or z. And the small m0 is actually the x bar, y bar, and z bar. So how about the midterm 6? The binary form of midterm, the binary form of 6 is actually the 1, 1, 0. So if the binary representation is a 1, 1, 0, then for the midterm is x bar, the x, y, and z bar. So for the max term, it's I'm sorry, I made a mistake here. So for the midterm, it's x, y, and z bar. So for the max term here, they are x bar, O, y bar, O, z. So if you want to understand each max term or midterm, you have to convert its index to its binary representations first. And in midterms, so if the binary representation, the corresponding bit of the binary representation is a 0, then you will have a complemented form of that variable. So if it's a 1, then you have a normal form of the variable. However, in the max terms, if the index bit, corresponding bit is a 0, then you have a normal form. If it's a 1, then you have a complemented form. So here is some example. So for this, in this table, when the index is a 1, we have the midterm. How can we have the max term? We can apply the De Morgan law. we can always apply the De Morgan law to convert the midterm to the max term and the max term to back to the midterm. So here is the De Morgan law. So X bar and Y bar equals to the X or Y, and then we have a large bar above that. Since the De Morgan law can handle n variables, then we can also handle n variables in by the midterm and the max term. And the capitalized mi is the complement form of the smaller mi. Then actually each row is corresponding to one midterm or max term. To one and only one. So we implement any function. We can implement any function by all in the midterm corresponding to one entries in the function or truth table. This is called the midterms of the function. We can also implement any function by ending the max terms corresponding to 0 entries in the truth table. This is called a max term of the function. Then in this case, we have two forms of the canonical forms. One is the sum of the midterm, sum of the product, or the product of the max terms, or product of the sum. So here is one example. We have two functions. The first one is f, the second one is g. Both of them have 3 variables as the input. So we just combine the two truth table, one for f, one for g, into one single truth table. So for the first 3 columns, these are the input variable A, B, and C. For the last 2 columns, we have the output of f and the output of g. Because we have 3 variables, then we have 2 to 3, which is 8 combinations, 8 input combinations. Then we can basically implement 2 circuits. One is for f, the other one is for g. Both of them have 3 input variables. And then we can write each function, f and g, as the sum of the product. So you can see we actually have a sign for the sum. So you can see that these are the sum. And this part is the product. The product is the midterm. And the number here are the index of the midterm. So the number here is actually the index of the row, which can generate a 1 as the output. For example, for the function g, for function f, the second row can output a 1. The second row has an index of 1. And then the row 5, row 6, and row 7. So totally we have 4 rows can give you a output 1. And for the function g, we have 5 rows, which can generate a 1. row 0, row 1, row 4, row 5, row 6. And then we can use the canonical form, particularly the sum of the product or sum of the midterm to represent these two functions. For the same function, for the same truth table, we can also write the function g and f in max term. How can we do that? We just pick up the rows which can generate a 0. So for f, row 0, row 2, row 3, row 4 can generate 0. So we just write their max term and try to AND them together. So this symbol actually is the product or the AND symbol. And this capitalized M indicates the max term. And then we can further write more details on the midterm and the max term. For example, we just translate this sum of the product or sum of the midterm of function f like this. And because we have 4 midterms in this equation, then we have 4 items here. The first item is the row 1. The row 1 has the input of 0, 0, 1. Because A and B are zeros, so we write the complement of A and the complement of B here. Because C is a 1 in this row, so we just write C here. This is the first term. You can use the same method to write the other terms. After we have the canonical form, the sum of the product, we can try to apply the laws that can simplify this equation. Eventually, we can simplify this equation, this f into b bar c and ab. And this simplified form is not canonical form. Why? Because we don't have all the variables in each term. And they may not follow the alpha beta order or the standard order. But by the simplified form, we can reduce the hardware overhead. On the contrary, it's difficult for the computer to compare. If we have 2 Boolean expressions, it's difficult for the computer to compare whether this simplified one is equal to the other one. But if both of them are in canonical form, particularly in the sum of the product or the sum of the midterm, it's very easy for the computer to compare them because they have a fixed order and they have a fixed representations. If they are the same, they must be, be the same. So again, the simplified representation can reduce the number of variables, the number of input, and hardware overhead. But the computer can do the comparison between 2 canonical forms. So this is detail of the product of the sum, the product of the max term. We can also do comparison on this max term, sum of the product of the sum form. And we can also apply laws to further simplify them. But after you apply a lot of law, eventually you can get the same simplified representations. Any questions? So in this lecture, we learned how to write the canonical form in both the sum of the product and the product of the sum for one single truth table. By the canonical form, the computer can actually compare whether two Boolean algebra or Boolean equation or Boolean function are the same or not. But again, if you directly to implement this canonical form by circuit by logic gates, then you will waste more hardware overhead. Then we can apply the loss to do the simplification and then get a simplified representation. We can use gates to implement that simplified representations. In this way, we can save hardware overhead. We can save gates, but unfortunately, it's difficult for the computer to do the comparison with the simplified representations. So now, in this lecture, we have to ask a human to apply laws to do the simplification. And in the next lecture, we will talk about how to ask a computer how to write an algorithm to do the simplification of the Boolean algebra. Thank you very much. Then we can stop today. Thank you.